Okay, great. Good to hear. Thanks, Cal. I appreciate that. Yeah, I don't think this is necessarily a technical talk. I don't think it would be suitable for the symposium. What it mostly is dealing with is exploration. We all explore. If you aren't exploring it, you're going to explore sooner or later. And we're going to end up focusing on the interpreting data in the deadband because there's a bit of ambiguity there, but there's enough anomalism on the property that we can actually start answering questions about it and its saliency and whether it actually exists, the response that we end up seeing. And the importance of it ends up being trying to explore in a region of the Athabasca Basin that isn't conducive to actually using traditional methods of time domain EM. In the Athabasca Basin, we typically try to map graphitic conductors in order to find uranium. And so that ends up being not only a metric used for exploration or a target, it actually ends up being a mechanism in which deposits form, because the rheological properties between the graphite and the politic zones that end up forming create voids and the deposits can form in them. But there are areas in the Athabasca Basin that do not have graphitic conductors. The western side of the Athabasca Basin is a really good example of that, where they are finding deposits that are not necessarily associated with graphite. And so we're starting to think that it's structure that's king, not necessarily graphite, but it does play in a very important role. So this particular project, Jansen Lakes, is located in what's known as the Magiatic Transition Zone. And it's right on the edge of the Williston Domain. And the Williston Domain is a set of quartzites and peelites and graphite that formed during rifting just as the Superior collision was occurring, or the Hudson orogeny. And a back arc basin opened up and allowed sediments to be deposited. And then as the collision continued on, we ended up with those units being folded and then eventually metamorphosed. And then on the periphery of it, we have the Magiatic Domain, which isn't as linear in terms of its structural compression, but and so we don't get these really nice folded graphitic units. Yeah, I think that's good. So the project itself is that black square in the upper left-hand corner, and it's in a pretty fruitful area. It's about 30 kilometers west of McArthur River Mine, which is one of the largest and richest uranium mines in the world. And it's also about 10 kilometers west of Pike Lake, which is a new discovery that's been discovered by Canalaska. There's also the Millennium deposit a little bit further to the south, which is Cameco, and then the Griffin deposits, which are Denison. So the area is fruitful. There's deposits around here. There's uranium. And yeah, so and in this, but as we get further west in this area, we get deeper into the Athabasca Basin, and the sandstone starts to become pretty thick. So not only are the graphitic conductors starting to disappear, the sandstone starting to get pretty thick. So we start looking for different techniques where we can start mapping possible alteration in the sandstone, which could be indicative of hydrothermal systems that drive these uranium deposits in their formation. Yeah, I think that's good. I think this is a really insightful and useful model to use at the beginning of the discussion, because what we're going to end up talking about is a number of the anomalism that we see on the property, and whether or not what we see in the ANT deadband is actually representative of something that we could be excited about or lends itself to the actual exploration model. And as you can see, we've got in this model, we end up with a politic unit with a graphitic sequence in the center. And as I've mentioned, there's a nice rheological contrast there. So if there's regional stresses, they're going to be released along those graphitic horizons because they're weak. And not only that, because there's also a rheological contrast between the basement and the sandstone, we end up with splaying of the structures. And so we have this situation where we have structures forming and likely fluids coming through from a deep source, and then entering into the sandstone column where we see pressure and temperature changes. So the role of the graphite not only allows us to have these structures form, but the idea is, and also lends itself to electromagnetic mapping so we can target them. There's also the thought that perhaps electrochemically it adds to the formation of the deposits, because it's thought that the uranium is transported as a uranyl 6 ion, and then as it gains electrons, it actually precipitates out and mineralizes as uranium 4 or urinal fluid. The model also ends up presenting the fact that you can have these periodic alterations. Now, the periodic unit itself can be high in magnesium and iron, so you can have these things forming up into the sandstone's column as these hydrothermal fluids are being transported up that graphitic fault. And so it's not unreasonable or unknown to have periodic alteration around a an intense clay alteration zone, where the sandstone has been dissolved and possibly whatever potassium feldspars are there can actually release potassium, and we'll discuss that in a little bit. It can also increase the porosity within the sandstone as well, so you can have uranium forming in the sandstone also. But the other thing I like about this model or this picture is that at the very top, we can see quaternary sediments in a dispersion trend that's leading away from an alteration zone, this oolitic kaolinite alteration zone. And whether or not you see kaolinite or illite at the surface depends really on where you're looking at that alteration zone and what the original temperature was. I think that's good. Next. So this is just simply to present the anomalism on the property as it stands. And so when we end up looking at the rest of the geophysical layers, you can give some meaning to what we end up looking at. One of the primary ones is what I call the Jansen Lakes geochemical anomaly, the JLGA, and that's in the blue box there. It ends up being a combination of lake bed and boulder geochemical anomalies, as well as airborne radiometric anomalies, and they coincide. And we had just seen in that schematic of the cartoon of uranium deposits where we can end up with these alteration systems and the transportation of that altered halo being transported with boulders. And what we'll see is a good combination or a good juxtaposition of both lake bed geochemical anomalies and airborne radiometric anomalies. Another important feature is the JLEA. Now, this is a fairly weak feature that I see in the VTEM and BTEM data, but it also correlates with the AMT that we'll end up discussing. It acts as a bit of a boundary. We also see correlation possibly in the magnetics as well. And the orange circle is not necessarily something of interest, but it's seen in the VTEM data and correlates with the AMT data, and it's shallow. It's in the sandstone. And in an indirect way, it ends up being a focus of this talk because it's what I think is actually showing up in the deadband of the AMT data. And now what exactly does it represent? I'm not entirely sure. I'm not saying it's perspective. I'm not saying it's uranium, certainly not. But it might add to the story of that there's a large hydrothermal system that actually exists here. Yeah, that's good. Okay, so, and as Kyle mentioned, this is actually my project. I picked this up. So I'm an explorationist. I like to, I think there's a lot to it. I've got a lot to learn. I've got to learn how to raise money and get a drill on the site. But these are the baby steps and we're getting there. But before we just had this recent uptick in uranium prices in the past maybe year and a half, I ended up picking up this property pretty quickly. I realized that there was open land and that the prices were going up and that the land was going to disappear. So I started looking. And one of the things I ended up identifying was in the magnetics. And I had mentioned before that we were actually operating on the transition of the Williston domain and the Mujatic. And the Williston domain is typified by this northeast, southwest lineaments, not lineaments, but structural presence. So that tends to be the dominant strike of the geology. And as we get into the Mujatic domain, that tends to be polyphasically deformed into more sort of dome and basin. But what we see in this area, that it's actually fairly strikingly northwest southeast. And if you combine these two structural components, you'll end up with dome and basin. So we're in this very sort of interesting transition area that where if you do have structures moving through, they're going to have to start turning. So this is an interesting zone that has probably a strike length of about 100 kilometers of this project. This project is only about 5 kilometers by 5 kilometers, but this entire area is of interest. And we'll end up looking at the actual survey coverage from the AMT survey from 2008. And you can see that it was thought to be interesting as well, because they've covered it with AMT to explore it. Now, one of the main reasons I ended up picking it up was actually because, and you may not notice, it's a fairly subtle magnetic anomaly. And to me, what I see is that we've actually got a bit of a load here that doesn't match anything on this side of the gravity features or on the other, although there is a small indent here, but it's pretty distinct. And so to me, it looked like an alteration zone. That's my first thought and first piece of interest. And also, another thing you can also notice in this diagram or this figure is actually that there are conductors along what would typically be the Williston domain, and they've been mapped out. So in the rest of the figures, you'll find out that these are all in the same spot, so you'll be able to keep your eye on where everything is. And then there's about 3 drill holes in through this area. One of the drill holes, OWL 02, this one up and through here, is one that we'll end up actually looking at a resistivity log and connecting it with the rest of the AMT data. The other important aspect of this figure is an interpretation of it, a fairly traditional interpretation of it, would be that we've got a bit of a small synform sitting here. This would be a large synform here, but this would be a smaller, shallow one here. And the same here as well. It's not quite exact because I think there's definitely remnants in the basement geology. So those anomalies aren't exactly representative of where you might see granitic and clitic units, but yeah, roughly that's what we go by. Or strokes. Okay, that's good. A lot of the data we'll actually end up looking at is from 2006 BHP, from the 2006 BHP Airborne Survey, Falcon Survey. There's a gravity and magnetic data set that are available that have quite a wide coverage. But I thought this was an interesting image after speaking about the geology and through this area, because the BHP system was able to combine both the magnetics and the gravity to come up with a pseudo-geology map. And I'm not entirely sure. I know BHP had SOMs or self-organizing maps in the early 2000s, and I'm pretty sure this is a self-organized map based on those components. And I think it does a fairly good job trying to indicate the fact that we've got these granitic units or antiforms with a synform of peatlites running down the center. So it does a fairly good job doing that. But it's also interesting to note that the bluer units are actually unsure. They're not entirely confident that these are actually granitic units, and it might be because they actually have a veneer of peatlites on them. So the moral of this, not the moral of this, but the message here is that we actually do possibly have peatlites that are sitting in through here. And with those peatlites, we may end up having, or metasediments, we may end up having graphite. So graphite might actually be present in through this area. They're just not vertical, and they're a little bit too deep to actually map with time domain EM. So from a traditional standpoint, this isn't an easy place to explore. So if somebody was to look at it and say, okay, are we going to spend $250,000 trying to put a drill hole in this? And what exactly are we going to target? And so it becomes very difficult. Orano has this property to the southeast, and the conductors over there have been targeted. But that's why they targeted it, because it has conductors, not necessarily because it's the best anomalous area. That's good. Thanks. Okay, so this is the first of 3 figures that we'll end up looking at that compare the boulder and lakebed geochemistry along with airborne radiometrics. This is the uranium channel along with uranium anomalies. I don't know if you can see them really all that well. They're the small triangles, small yellow triangles, and they tend to be a bit larger in through this area and more numerous in through this area here, and not so much in through here. And you also end up with a slight uranium anomaly as well. And the idea here is that we've actually have a glacial erosion, and it's plucking up lakebed material, or not lakebed material, because it wasn't even a lake at the time. But let's say there's a structural zone through here, which is actually fairly believable because we have a number of lakes that are actually situated there. The entire area has been glaciated, and plucking ends up occurring. And often it's not unusual to see lakes forming where the sandstone has been plucked and mobilized. And so we can have a stream of the material from the lakebed and anomalies both in the lake and boulders up on land. In particular, we have only one boulder up on land that actually ends up being somewhat anomalous in uranium, and that'll become a little bit more important later. But that's good. Thanks. So that uranium anomaly is also coincident with the potassium anomaly. So not only is there uranium that's anomalous, both coincident with the lakes. Again, we have elevated lake bed geochemistry, but we also have radiometrics in potassium. We have radiometric anomaly in the potassium. So again, it's giving this impression that we have this alteration system that has developed along a structural zone that's represented by the lakes, and that's been plucked and dragged in the system here. But we have anomalies here. Yeah, that's good. Same thing with thorium. So we see the same thing with thorium, a little bit more impressive. I think the stands out quite a bit more that we have these thorium anomalies and that we have this a little bit more subtle than radiometrics, but you can still see it. And you'll notice that that small boulder has disappeared. And that's interesting to me. So there's a boulder that was high in uranium and potassium, but not necessarily thorium. That's of interest to me. It's sort of suggesting to me that we have two sources. We may have, not only do we have plucking from this area where I suspect there's structure along those lakes, along the Jansen Lakes, but also the area around the center of the zone of interest is actually altered itself as well. Now, we can also look at vanadium and iron. And I had mentioned earlier that it's not uncommon to see alteration systems that are high in iron because when the structures move through these polytic units, they're mobilizing the iron and the magnesium from those units. And so it's quite common to see iron in the hydrothermal system or adjacent to it. What's unusual is the fact that we have these vanadium anomalies and very low iron. And so what I'm thinking this is representing is that, yes, we're in a hydrothermal system, but that alteration system and those fluids are low in iron and they're high in vanadium, which to me sound like a deep granitic source. So we have a structure that's passing through a source and goes quite deep to create hot enough fluids to come up 900 meters into the sandstone and push out any iron that's in the sandstone, and also doesn't have any iron itself, but is high in vanadium. So to me, it sounded like a deep-seated granitic basement source. You can also take a look at the hyperspectral data, and the geos are pretty good at this. When they go out and they do their field work, they use quite a bit of boulder sampling and taking hyperspectral, looking at clay speciation and mapping it out. And I myself am not too particular about the type of clay I see. I just want to see transitions and I want to see changes. And what I see is we're dominated by dickite, that's the green, and then we end up having a bit of kaolinite and illite in the area that we're somewhat interested in. But the area seems to have expanded. There seems to be a fairly large area that has this transition of kaolinite to illite to dickite. And in particular, it doesn't show up as well on here, but it still looks good. There's a very nice transition in through the zone of interest. And this is most likely representative of the basement rock, just because of its continuity. It's not mottled, it's fairly continuous. I would say that's actually probably from not plucking from the sandstone basement local, not necessarily transfer. Yeah, I think that's good. Okay, so this is another data layer that we have. It's the airborne gravity. And there are two primary things that I see in this. And one is this gravity high that we have to the southwest, and we have this low to the northeast. And it's also has quite a bit of high frequency component to it, possibly due to the drumlins in the area. And it's a little difficult to integrate into the story unless one considers this gravity load to be represented by a structural zone that's come up. And this is the structure here that's subcropping, and there's an increased degree of secondary porosity, which is lowering the density. So you have a slight gravity low. And then to the southwest, we have this gravity high ridge. And that gravity high ridge, maybe it's represented by sort of thermal dispersion of matter within sort of mass dispersion within the sandstone itself. And as it heated up, it pushed iron out. And but we'll end up looking at this again, because what I do is I upward continue it about 500 meters so we can have another look at it and try to get rid of this high frequency component and compare it to a couple other layers to see if we can get something more out of it. I don't generally tend to look at a lot of airborne gravity in the Athabasca Basin. I tend to think it's kind of shallow looking. It's looking mostly at the sandstone, I tend to think. But we'll discuss this later. Yeah, that's good. Okay, I promised we would actually have a little bit of Z10 data. There's just a very small part of Z10 data right here. It's represented by a 3D inversion that's been threshold into a voxel in two ways. One is at high resistivity, above 8,000 ohms, and that's this zone here. And it looks like a little dome in the inversion. The Z10 survey pretty much stopped right here, right where the model stops. And so we're limited to comparing the rest of the data with that section of the voxel. The other part of the voxel I threshold was below 1,000 ohm meters, and that's this zone through here, this yellow and green bit. And it looks to me a bit like a shallow synform, so it kind of fits that model. But is that just playing with thresholds and making it fit? I'm not too sure. The JLEA does, however, that Jansen Lake electrical anomaly is this white dot, and it does line up fairly nicely. I think this is the first time we actually end up seeing the AMT data. So this is our first sort of connection with the AMT data during this talk. And the inversion itself was performed below 1,000 hertz. And it wasn't, and the data that was available from the assessment files was only maps, paper figures. So these are geolocated images, both the map itself, that depth slice that you see to the right there, it's about 150 meters above the unconformity. And just within, coincident with the zone of interest, we end up with it's a slight resistive low. It's nothing super impressive, but it exists. And along with it exists this extension, a slight resistive low moving up to the northwest as well. The triangles are the actual AMT stations themselves, and we'll take a look at a few of them. What else can I say? But I don't know if you noticed, but there's a really nice correlation in the 3D section that shows possibly a structural zone reaching out towards the surface. And this area here is, in fact, where we have our lake bed geochemical anomaly. So you can almost stop right there and say, well, this is looking very prospective. This is worth looking into more. So at this point, I was pretty happy with the fact that the property that I had picked up and that things are looking fairly good. Yeah, we'll leave it at that. Okay. Okay. So these are the AMT parameters when the data was collected. When I went through the data to try to find out whether or not the responses in the deadband were actually real or not, I was looking at the K factor to try to find out if actually they corresponded with days that we had fairly high activity in the horizontal magnetic field. And it correlated fairly well. The contractor had repeated it a couple of stations. There were a couple of bad days, but typically the data looked fairly coherent. And you can, and on the far left, or on the right, you'll see that in the inversion parameters, they only used 8 frequencies, and they're all below 1,000 hertz. The grid in the center is a depth slice. So it's about it's just below the last depth slice we saw. This is at 1,000 meters from surface, and you'll see the extent of it. It's a fairly large survey. It's about 490 stations, and the area that we're looking at looks far less convincing than some other areas that we have in terms of conductivity. So it's no wonder that the area was passed by on this, and that other areas with better metrics were actually continued on with. Okay, I think that's good. So this is the resistivity log that I had spoken about in AL 002, and it's fairly representative of the sandstone column, where we have the MFD in the upper 400 meters or so. And the MFD tends to be this quartz arenite that's fairly tight and relatively resistive. And in this resistivity log, we're seeing resistances between 8,000 and 5,000 ohm meters. And then we get into the MFC, and the MFC it's a log figure, so it's the expression isn't as emphasized, but there is a little bit more conductivity in the MFC, and we'll get to that later. The MFC tends to be this pebbly bed with maybe a bit of clay in it as well. So maybe that's what's showing up in the AMT. And then as we get deeper into the MFC, we're starting to see more coarse sediments and a bit more porosity. So the resistivity actually decreases just slightly down to around 3,500, 3,000 ohm meters. And in the basement, in that particular hole, LOO2, and they were targeting a conductor and they hit it. Not a very good one, but they hit it. And when I model it, we get a fairly typical response of what we see in the Athabasca Basin in terms of an AMT model, using the same frequencies that we use in the survey. And what I want to point out is just how smooth everything is. And this was done with a 1D model, so you kind of expect that. But when I tried to model a shallower, thinner layer with higher conductance, I wasn't able to produce what I see in the deadband. And we'll get to that in a second. I know we haven't seen it yet. But yeah, I think that's fine. So let's look at the data. So what are we talking about? This data in the deadband that's causing so much interest that we have to deal with. The first one looks like noise. That looks noisy too. So just right off the bat, that looks like noisy AMT data to me in the first, and one of the first soundings. This is the apparent resistivity and the phase. But there are other responses throughout the survey area that have these controlled dips in them. Even that looks almost like noise. I don't necessarily see AMT data or MT data that changes that quickly in terms of resistivity. Usually they are fairly smooth. So this is curious to me. But then we get into other areas within the AMT deadband above 1,000 hertz. This is in period by the way. So we're increasing in terms of the actual lowering frequency out this way and looking deeper this way towards the left, the right of the figure. But we end up with some pretty complex responses. Some of them with phases that are negative, which is sometimes indicative of just resistive geology. But I sometimes wonder if some of these responses are related to possibly chargeability as well. A typical response that we see is this one here. This is a fairly typical response where we have a fairly controlled decrease in the resistivity and an increase. And now the deadband is called the deadband because the energy within that frequency band tends to be quite low because of the reflections off the bottom of the ionosphere at certain times of the day and certain times of the year. And so certain frequencies are muted. And so the signal should be low. So if there's noise within the deadband, you would expect noise in the apparent resistivity as well. And that doesn't look noisy to me. That doesn't look like noise. That doesn't look like noise. That definitely doesn't look like noise, the way the phase changes. And so you see this repeated across a number of the actual stations where we have this dip and we have a very similar change in the actual phase. That's not noise, in my opinion. So now I ended up actually asking a number of colleagues over the years. It's been 2 years since I've been working on this. And I would explain to them, I have this data. I have this AMT data. I have this response in the deadband between about 1,200 and about 4,000 hertz. And they're like, nah, just forget about it. Just forget about it. It's just noise. It's probably just noise. Don't worry about it. It's of no interest. And I kept looking at it, and because of the coherency, I would just visually, I would say that it's quite real. And what we'll end up doing is comparing this response with the other parameters that we have to try to build a story about whether or not it actually represents something or if it is actually noise. On the right hand side, we see these colored images of the decreasing frequency as and the apparent resistivity. And sorry, there's no color bar, but red is resistive and blue is less resistive. And we end up with some complexity in certain areas. And you'll notice that actually the resistivity zones and as we get deeper, we start to develop these conductive zones and resistive highs among them. And in particular, in a particular area, in the zone of interest, we end up with these really complex responses. And again, I tend to think that's pyrite, or maybe some sort of IP response, but I'm not entirely sure. But you know, I do have some cognitive dissonance on this. How can it change that fast? How can the frequency responses change that fast? Because these frequencies they're not particular to a certain depth. They're interacting with the geology over a wide range of depths. And so to have it quickly change like that, it's peculiar. It is really weird. So it's something that I'm going to have to continue sort of investigating. And I think probably the best way to do it is to go out and do repeat measurements. let's try this again. Let's get the same equipment. I believe this was Phoenix equipment that was used. Let's just get the same equipment, rent some equipment, get out there, take 5 or 6 readings to see if this thing's actually real. Okay, that's good. Okay. So I tried modeling in 1D. I wasn't able to reproduce those kinds of really intense changes in resistivity. And I tried to do it in 2D. So I created a model that had an 8 kilo ohm half space with a 1 Siemens or 1 ohm conductor within it that was isolated with varying thicknesses, all the way from about 200 meters to 300 meters wide, and increasingly brought it to the surface to see if I could see the response and what sort of response it would create. And I got pretty much what I thought I would see. These very smooth responses, really smooth responses. I am unable in the 2D models to create this very distinct change at about, I think it's about 4,000, 3,500 kilohertz. So yeah, it's strange. Okay, so what's my alternative? If I can't invert this data, if I can't try to reproduce this, what else can I do with the data? And one of the things I can do is calculate the dimensionality. And the dimensionality will give me an idea of the complexity of the resistivity contrast laterally within that area. And perhaps if I can see some continuity, I can put together a story about that this data actually has some meaning. And one of the things I like is this image here, where we have this horizontal magnetic field that's our source, that's going into the Earth, into the system, and out of the system we get our horizontal E fields and our vertical magnetic field. The data that was reported or delivered in the assessment reports didn't have the HZ, so we can't do a tipper. So we're stuck using EX and EY, or stuck using the apparent resistivities and phases. But from those, we can calculate the impedances. And the impedances are complex, and so we can rotate them, and we can see how the resistivity changes as we rotate them. And we can create these Rose diagrams that compare both the XY component and the XX component. And if the XY component is nice and circular and the XX component is really small, we're probably dealing with a 1D Earth. And if we have an ovoid or an elongated XY and a somewhat complex XX, then we possibly have a 2D geology. And if we have both are very complex, then we probably have 3D geology. And on these diagrams, I've put an arrow in the direction of the XY's lowest resistivity, and that should give us an idea of the strike direction of the conductivity or the low resistivity that we're dealing with. And now it's important to remember that in 1D, the arrow doesn't really mean very much, if anything at all. And in the 2D, yeah, it's possibly pointing in the direction of, in the 2D and the 3D, possibly pointing in the direction of our geological strike. That's what I say about that. The other thing is that the arrow is not necessarily, it's actually should be pointing in both directions, because there's a bit of ambiguity about which direction it's actually going. Okay, that's good. Okay, so I can take all of these and I can try to put them in a profile and see if I can find some structure, see if I can find some correlation between them. These are some examples that we have across this particular line. This is line 22. You might not be able to see it very well, but it's about here. This is what the GLEA is based on. It's this sort of late time, mid times. We'll say it's mid times. It's actually mid time, maybe late mid time. 810 microseconds in the V10 data. And we get a fairly nice trend that shows up. And it's on that trend that we can actually start to see boundaries in AMT data as well. This is the apparent resistivity. And I know it's yellow and blue. It's yellow is conductive, blue is resistive. And then we have the phase below it. In hindsight, I probably should have calculated what's known as a Bostic resistivity and combined them. But when I created these, I wanted to start from scratch and just look at the apparent resistivity and the phases separately. And then I was planning on doing the Bostic, but I never got to it. And then in this panel down in the lower right-hand corner, we have the airborne Falcon magnetic data calculated the analytical signal along line. So that's a grid of the analytical signal calculated from the line data itself. And it's a fairly good product. I won't try to explain too much about it, but we'll discuss some structure that I end up seeing in it or seems apparent. So what we're looking for in this diagram is any sort of like continuity in some of these dimensionality plots. Are we seeing consistent 1D Earth? Are we consistently seeing a 2D Earth? Are we seeing a 3D Earth? And I have to admit, it's pretty hard in this figure. It's not as the response in this area isn't as distinct as we see in other lines that we'll end up looking at. But it does show something fairly common that we see throughout this area, and that is that we have this increasingly conductive zone that ends up at the end of it creating this layer in the upper sandstone, or at least in a shallow feature in the sandstone. Okay, I think that's good. Along line 21, it becomes a little bit easier to try to interpret continuity between them. I think it's fairly consistent with the 1D Earth on this side and above in the higher frequencies. But there is also a distinct zone where we end up with 2 to 3D. It looks like 3D, three-dimensional structure. And it becomes that continuity from line to line gives me a sense of confidence that this exists and that it's shaped somewhat like up and over. There's something, that's the shape. It's like this-ish, which that's about all I can say about that. And again, there are some stations that just looks noisy all on its own. That doesn't look like noise. Okay. But there are areas where if this is line 207, it actually ends up being in a fairly important spot where we have the zone of interest and a lot of this anomalous that's actually occurring. One of the things that are on this diagram that might be a little bit hard for you to see, and perhaps I should have made the line a little bit thicker, is actually this ovoid zone here. And this ovoid zone shows up in the VTEM data that we'll see in a couple of seconds. So there is a correlation between this feature and the VTEM data that's been collected over the area. That's good. And so in the VTEM data, in the early time channels, we do see this feature developing, and it's fairly consistent. But once we get to about 480 microseconds, this is after a directional cosine filter, we end up with a fairly, we end up with something that kind of looks like the geology we were expecting, where we have this somewhat of an antiform on either side, and maybe a synform in the center that's a little bit more conductive. This zone here, this basement resistor, is transported over to this magnetic anomaly map, airborne, that has been upward continued 500 meters. And there's a couple of interesting things that I see in it. One is that, yes, we still have this gravity low to the northeast, but we also see an intensification directly over what we were interpreting to be a colitic unit, but not along its entire length, but coincident with our anomalism, both in the V10, the upper sandstone, but also with that JLEA in the basement. Yeah, I think this is a good time. I think this is the only image, if you can go back one. This is the only image I have of the structure. So regionally, if I end up analyzing or taking a look at the analytical signal that was calculated for this region, there are two regional structures that show up. I'm not a big fan of just drawing lines across a map. I try to stay away from it, but you can't get around it sometimes. But there is fairly good continuity between two structures that bound that area to the north and the south. And in my mind, anything that has a long strike length probably has a deep source, or it goes quite deep. If it's long, it's probably deep. And so those features seem to exist. Now, the model I'm playing with at the moment, that this is a wrench fault system, and that within that wrench fault system, we have the development of a Riddell shear. And that Riddell shear is creating dilations along its length. So even that JLEA that I've pointed out, that trend, may not be an actual fault that's come up, but rather a series of dilations. And this is good because we want dilations. We want a place to put uranium. And we also want something close to a deep-seated source. And so we have a deep-seated structure, possibly, that's feeding dilation zones in our zone of interest. So in the end, the JLEA, this conductor that I see in the V10 data, correlates with the western edge of the southwestern edge of this conductive anomaly we see in the AMT data, and with the V10 anomaly that we see in the shallower parts of the sandstone. Okay, that's good. Okay, discussion. The AMT dead band anomalies that I'm seeing, they look real. Okay, I haven't done any mathematical tricks here. I've just gone through all the rest of the data and tried to link things, and they seem to all correlate. So to me, it looks real. The attempt to try to model these in 1D and 2D failed, and which means they're probably not invertible. So even though it exists, it looks as if it exists, if you try to invert it, it would probably fail, although I haven't tried to model it in 3D. We went to dimensionality to help determine the existence of the electrical anomaly and its bounds, and to also to understand its structure. We developed confidence in the intense alteration zone enhanced by the AMT, and I tend to think that we may be seeing IP effects in that deadband. And what I didn't describe in the 2D models was actually that we tend to see conductive anomalies offline to quite a distance. And so I was pretty impressed by that. You don't necessarily have to be directly over a conductive source to see it in the AMT data. You can be offline. And from an exploration standpoint, this becomes important because of the cost. So you can have a wider station spacing and still be able to invert it and retrieve a usable model. And as a conclusion, the modeling and inversion code's approximate and not always applicable. And sometimes we have to go to reason and anomaly stacking in order to interpret things. Alteration is likely structurally controlled and possibly invasive into porous media within the sandstone column. So I've been describing this ovoid feature. It may not necessarily be an ovoid feature, but it could be an invasion of fluids within the MFC, or it can be a combination of structural complexity within that area. And so really, as I mentioned before, to confirm all this, I'm going to have to actually go out and collect a few more stations and make sure that the AMT data is actually real. And so the AMT is used for exploring in deep zones of the Athabasca Basin where time domain EM, traditional time domain EM does not work. And it's a good, and I think this project was a good example of anomaly stacking to gain confidence when dealing with ambiguity. And that's it.
Have questions? Yeah.
Yeah.
Anyone online want to unmute themselves?
That was only half an hour.
We have time. It's okay. You don't have to run.
I have one. So yeah, you got a lot of really useful information from the, I guess, surface geochemistry and radiometrics. How high above the unconformity does that alteration zone typically end up, like 100, 200, 300 meters?
That's the very question. Something I forgot to mention, actually. It does seem a little bit detached from what we would expect from a hydrothermal system in the basement. We'd expect something coming off the basement to be about maybe 300 meters off the basement. But if you have these an intense structural zone, the fluids are going to be pushed up into through the structures, and it's going to have a much easier time reaching up into the higher reaches of the sandstone column. I think one of the things I don't really like, there's a lot of details here that need to be worked out. For example, where we have this geochemical anomaly close to the surface, and we see in the AMT inversion that we have possibly a connection between the basement. It looks like a connection between the basement and the surface where these fluids can move up. It's difficult to explain the sequence of events that created the anomaly that we see. One of the ideas I had was that the sandstone was still developing while this was occurring. So you can think of it as the sandstone's there, it's still being deposited, but a structural event occurred which caused fluids to come to the surface and deposit clay. And so you've got these like puddles or lakes of hydrothermal fluids, hot springs, let's say. And but that doesn't explain if you have it covered over again, because we still have another 200 meters or so of sandstone that are above that. How do we get some sort of hydraulic connection above that? And the only answer to that is that we have a reactivation of that fault, and that caused it. Or we instead have structure that's moving up through the sandstone column and invading the strata. And that's the strata is being altered, and that's why we see this conductive anomaly in sandstone. And so there is, even during that hydrothermal event, the sandstone column was there and being pushed 900 meters up into the sandstone. So Yeah, it'd be a big system. It'd be a really big system. And what's interesting is that we see the most intense part of it. We see it along the strike length of the property, but we see it most intensely where it subcrops into that lake, and we see this dispersion of geochemical anomalies. But it's that area tends to be also coincident where we could possibly have a connection with a deeper structure. So there's different classes of structure in the basement. Not all of them go really deep. And you kind of want to have a hydraulic connection with that and move fluids in. I don't know if that, yeah, I think that answers your question.
Yes, I was just thinking kind of the thought process in sort of this area of the basin, which is more towards the east, a bit shallower, and you can sort of do these things, and then kind of how you encounter challenges when you start to move to portions of the basin that are a lot deeper, and then perhaps you don't have the alteration that gets to the surface, and kind of just getting a sense of how much of a hindrance that would be as we start to look at deeper portions of the basin.
This is about as deep as it gets. It doesn't get too much deeper than this, maybe a couple hundred more meters. So this is about as deep as it gets.
Oh, so yes, that alteration, even in very deep parts of the basin, can actually give you surface geochemistry information.
That's what it's looking like. So it's a fairly large system. And yeah, I think that's a good point. Like, it's a good point to point out that this is a fairly deep emphasizing. I should be emphasizing a little bit more how one of the catches I tried to promote this talk on was sort of like opening up a new area of exploration, right? And that's in this Mujadic zone. We're seeing a lot more ZTEM. We're seeing a lot more mobile MT. And these do a fairly good job of mapping broadly conductors in the basement. But in my opinion, the ZTEM system uses too low frequency to actually investigate the sandstone. And the mobile MT tends to be a bit lacking in frequency content, even though that's their selling point. So sometimes it has the frequencies available to you, sometimes it doesn't. And there's other issues there as well, I think, in terms of what they're using as a primary field or what they're monitoring as a primary field. And I can get into a discussion about that if anybody wanted to. But so we're seeing a lot of natural source airborne systems that are kind of approximate-ish. There's something ish happening here. What I'm finding is that the AMT is a really nice technique. It's a surgical technique. I think it's a surgical EM technique, and I'm warming up to it. And I think there's a lot to it. It's going to take me quite a while to become more proficient with it, to use it more effectively. But even in an exploration, if you only have a couple of man crew, you can do something. You don't need to pull 5 kilometers of wire through the bush. You don't need to cut lines. You still have to wait at a site. You still have to carry some heavy equipment, but you can set it up, let it run overnight, or maybe you can hopscotch equipment if you have a couple of receivers. So I think as an exploration tool, AMT is a really nice tool, especially if you start considering controlled source AMT. And that's one of the things I'm considering for this project as well. I think controlled source would be something nice to.
Yeah, and if you're interested in alteration, I'm wondering if you've heard of any of the applications of ambient noise tomography. So that's something that they're using that actually is sensitive to the alteration zone, and they're using that to direct.
Yeah, no, I totally agree. The ambient noise tomography has issues as well because you need a source, right? And usually you need these large bodies of water to actually be your source. So you kind of have to be east-west of a large water body for that technique to work really, really well. And but yeah, I think that's definitely another. There's a lot of exploration positives with that as well, because you can go out into the field, lay them out, leave, come back, pick them up, move them. And so just from a cost standpoint, you don't necessarily have to put in a permanent camp for a month. You can just get a couple of guys out there, get a helicopter for a couple of days, slime these things into the ground, get out of there, come back 3 weeks later, collect them, and make the data. So yeah, I think ANT is a great technique as well.
Alan, do you want to unmute yourself and ask your question?
Yeah, hi. I really enjoyed your talk. Thanks very much for that. Great overview of the basin and the different techniques. I think though that you're on a bit of a wild goose chase with this AMT deadband, because it's noise, you know. So you're modeling noise there. I see that all the time with daytime AMT recordings, that you get this dropout in the apparent resistivity. And that's because the way that the apparent resistivities are estimated are that they're downward biased by noise, and that's exactly what you're getting. If you were to take those time series and take the E field as your remote reference, you'd find an upward biasing. You'd find them, the apparent resistivities going up in the deadband. And so those dropouts that you're seeing and the weird phases, I mean, one thing that's important to know is that the apparent resistivities and phases are not independent, they're related to each other by a Hilbert transform. And so you can actually run a Hilbert transform over these, and you can just show to yourself what data you will never, ever be able to model in any dimension because they're not consistent with the Hilbert transform relationship. And those ones are clearly inconsistent, and you cannot get apparent resistivities dropping by 2 orders of magnitude within half a decade as you've done. So please carry on with everything else you're doing, but have finding meaning in the AMT deadband. Unless you've got some overnight recordings with decent data, those big dropouts are just noise.
Yeah, I think my ignorance is the burden. That's be true.
Yeah.
And I think I have to be able to be open to you being wrong, and in some way, and that's okay. And as I mentioned, I'm open to me being completely wrong. I have to do more measurements. I'd have to repeat a few stations to see if I'm able to repeat it. But I agree. It seems really incomprehensible that the resistivities would drop so fast. I don't have a technical reason. You've given me a technical reason for that. And but I am also open to you being wrong. And I hope you don't take offense to that.
No. I mean, I've only got 50 years in MT, and I've been wrong about.
I
other
understand
things.
that. I completely understand that. I completely understand that.
Alan,
But, yeah.
Alan, it's Dennis Woods here.
Hi, Dennis.
Be nice, will you?
I'm trying, Dennis. You can't see me laughing.
Dr. Johns, I was hoping you'd be on the conference call and see this and call me out on it. That's exactly what I needed to hear.
Yeah.
Was that it's bullshit.
Well, that system, I believe, the 2008. You said they're required by Geosystem, so that would have been recorded by Gary Mathieson, who retired now, lives not far from me, and he was using Matronics gear, I think, at the time. Now, Matronics have very, very good AMT coils, but what lets the system down is their time series processing. And so if you, I don't know whether you'll be able to get that time series data, but it might be worthwhile getting the time series data and then having the data reprocessed using modern algorithms. And that can help you to try and get better estimates. And the other thing that you can do, that the shape of the Hilbert transform is such that, you might have, let's say you've got bad data at 2 hertz in apparent resistivity, but your 10 to 5 hertz, 2 kilohertz, your 10 kilohertz to 5 kilohertz, and then your 1 kilohertz to 500 hertz in your phase, they will predict what your 2 kilohertz apparent resistivity should be. And so you can use this Hilbert transform relationship to do some predictions in the gap. And that you can then take forward to do, robust 3D inversions.
Okay, and it seems more reasonable that it's not real as opposed to some, lack of a better word, exotic electro mechanism. So I'm open to it. And I think in this case, what I'm trying to do is explore its validity, its relationship with the rest of the anomalism. It seems to fit, but at the same time, maybe it's just coincidence, or it is just noise. But I'm not too sure. It's not something I'd end up focusing on, and it's not something that I would try to sell the project on. It's just a matter of trying to understand that data. And what was getting me was the coherence. Just the fact that I see the same thing over and over again, including the change in the phase. And so how does that happen from station to station or from line to line? And I can't fathom, I can't understand that. So it's just gonna take me some time to gain confidence in in the known science. And I know, I know someone with your experience, you are solidified in your determination of what's possible. And man, I appreciate that. And that will obviously guide me to whatever I do next, which probably isn't going to be too much in terms of the AMT after I've listened to it. But I'm still going to be thinking about it, and I'm going to be open to it.
Yeah.
And if I come across something similar again, I'm probably going to try to test it. And but you're right, I should probably get more into the theoretics and how the Hilbert transform can be applied to test it. And yeah, so thank you very much.
Yeah, I don't know if you've read our paper on atmospheric sources, the Garcia and Jones paper.
I have, yes.
You have?
Yes.
Yes. Because I mean, you referred there to the K indices,
Yes.
but the K index is a measure of solar activity, and that's low frequency activity below 8 hertz.
Yeah, it's not necessarily AMT bands. Yeah, fair enough.
No, but the one thing it could do, I mean, if you got a high K index, then you're getting higher solar ionization of the atmosphere, which will lead to a higher attenuation of the energy from distant lightning storms, which will lead to lower signal. And so, if anything, you should see an anti-correlation of your K index and your signal strength.
Okay, very good. Hey, thank you. Yeah, I think you're just hitting me over the head with reality, and that's great. And the thing is that I will take those bumps and yeah, just move on. Yeah.
No, I'll be pleased to give you advice if you want to just send me an email and we can chat later.
Hey, that'd be great. Thank you very much.
Sure. And again, great talk. Thank you.
Zoe, did you want to ask your question in person, or I can read it out loud? Okay, well, Zoe said great talk.
Oh.
Do you think static shifts might have affected your dimensionality analysis?
You know, I was looking for it in the data, and how do you look for it? I mean, I think Dr. Jones just exposed my my experience level with this. But my understanding, the DC shift ends up you would see it from station to station as offsets, just simply because of the grounding of your electrical components that you're measuring. And I was trying to keep an eye out for it. I don't have an eye for the data. Could it have affected the dimensionality plots themselves? Well, the dimensionality plots were essentially measuring anisotropy to a certain degree, and I would imagine that the resistivity would. I don't think the qualitative shape would have been affected. I think the actual apparent resistivities would have been affected. So actually what I'm thinking at the moment is looking at the dimensionality plots gets you past static problem, I would imagine. I don't know if Dr. Jones or mine or if anybody in this room has another comment about that, but no, is that no? Anybody?
I don't know.
But that would be my immediate thought on that.
Okay. That's good. That's all online. Anyone else here?
Yeah.
Right on.
I'm going to be a little bit nicer than Dr. Jones. First of all, it was a great talk, and I particularly like bringing geology together. This room's geophysicists, but we heard a talk that was mostly geology, right? And half of it I didn't understand. I'm sure the rest of you are in the same boat. It's great to bring geology together. And so much geophysics, you know, wide variety of things, all rolled up into one geological explanation. So that's a great part of it. You're both the consultant and the client on this particular project, right? Let's pretend I'm the client.
Sure.
And you're the consultant. Where do you spot the first drill hole? Pull a map up here and point to the first drill hole.
Yeah, I think if you back up 2 slides, I would put probably the first drill hole down that you can say it's here where we have we have a coincidence between what looks to be east-west structure. That structure continues on towards towards a newer deposit that's just been found off to the west or off to the east side. And as I mentioned, there could be possibly a dilation of zones in through there. So the first, I would be trying to look close to any sort of anomalies in the basement in through this area. That's what I would be doing.
And your first plots you showed with the circles, the ellipsoids around, so that's in the middle of those, is it? That
Just a little
spot?
bit, just a little bit to the south, just a little bit to the south, east, just a little bit to the southeast. But where it is, it's actually located, if you go back to fairly close to the beginning where we actually end up looking, just down where we have the Z10 data.
Oh, you bypassed it?
Yeah, and I mean, this, in terms of deposit development and uranium exploration, we often look for structures that are coming up against these domes. Again, because of these rheological conditions where we have the rock actually cracking and breaking at these contacts. And we have this dome that's situated here, and then just on the edge of it, we have this conductive anomaly that's seen below 1 kilohertz, so it's not affected by any of that AMT, we'll call it noise now, that we see. So yeah, this is definitely, and then just above it, that's our zone of interest, right? Zone of interest is right over here. So essentially just a little bit further to the south, down structure.
I just got to raise a quarter million.
Yeah, exactly.
Yeah, I think actually AMT is probably one of the things I'd like to actually deploy. Next.
Tyler, I'm just sitting here witnessing this and I think this is actually like a beautiful thing here because, we have someone like yourself that's passionate enough to put all this together on a project that you own and to look at all this data and put it together. And we can broadcast this live and have someone like Alan Jones, who has looked at MT data for 50 years and spot this out and give you some insight on the why. I think that's a beautiful thing. And I want to, commend our community for that. And Dennis, I think Alan was nice about it. He wasn't.
Yeah,
And, but I think, like where Dennis was going with this is, that's the challenge now, Tyler, for you is that, you need to raise some money and talk to some investors and geologists to get out and drill this, right? And so like, what are the next steps in your mind? You talked about collecting some more MT data and probably having Alan take a look at it and consulting with him would be a great idea. But are you still thinking, is that the next step here? What else would you do? What else do you think you need to do to get to the point where you can drill this and either sterilize it or prove it up in terms of its uranium potential?
Yeah, I think there's two strategies there. One is, yes, I'd like to move forward, do some more geophysics. I'd like to do some more AMT. I'm still interested in testing this out. And let's say it was noise. Well, damn it, let's collect some data that doesn't have noise and see if we can invert that and get a better handle on the structure and the alteration that we possibly have in the sandstone that's indicated in other layers. The other thing that I need to do is buy time. So the thing is that I have competitors that are around me, and they have deep pockets. They have about $12 million to be exploring through this area, and there's anomalies. So what I'm waiting for, I just need to buy time until they drill a hole and they find something. And then if they find something and I've got metrics, I've just got to hang out. I just got to hang in there, and then it's an easy sell, right? Somebody will either approach me or I'll be able to pitch it fairly easily. You'll notice actually, and if you go up one slide, there's actually one more slide.
Oh, the doorway.
Or down, actually, yeah, here. There's actually a couple of anomalies that show up. The area, the surrounding area, other than mine, was just flown with mobile NT. And this anomaly is just shown. And I wasn't too sure about the validity of this anomaly in the southwest. But, after doing the modeling in 2D and seeing that you can have your stations further off and still be able to image basement conductivity contrast or low resistivity zone, yeah, I'm confident that this actually exists. So I'm just waiting for someone to drill it. Now, much of this presentation was actually done on figures and work I had done for the assessment report. And as far as I understand, I'm one of the first people that actually was able to submit an assessment report in Saskatchewan based purely on historical data. And I got about $60,000 worth of value out of that work. So now I've got one more year to try to put in another $60,000 worth of data. So I've got to figure something out. I got to hang in there. I've got a couple of strategies that I haven't necessarily released just yet, but yeah, I have to do some more work.
Your claims are only good for a year?
You get the first 2 years,
Okay,
and then you get it's every year after that.
you have to spend how much?
I spend about $55,000 to $60,000 on what to try to reduce the size of the prospect. The problem with reducing the size of the prospect is that people see value in scale because they see potential on large land packages, because then there's a greater probability of finding something. So investors want to see scale. And so I don't want to reduce the size of it. What I want is my competitors to find something. I want even since it's scale. So and that'll boost me growth. Just got to hang in there for 2
On that note, thank you.
years.